soon. So here are the specifications: the noise floor, the frequency at which the floor is measured. This is 30 megahertz. That is our highest frequency of interest. The length of the antenna, the radius of the antenna, and a number of widths that I want to use for evaluating the length and the drain current of the MOSFET. So the width is not a parameter that I want to design. I just give it, and I want to get the result for the other ones. This is just a parameter that is not interesting. It's unity, so for the moment. Then I create a project, and I run the antenna circuit in order to get the variable, the antenna capacitance from the program itself. That's what I would like to have. And you see, I define the parameter L, which is the length of the antenna, the radius of the antenna, and then I let the program calculate the antenna capacitance and put it in the variable CA, which is here on line 29. And then there is the total capacitance effectively that I have in the input in parallel with the input, because CF was L times CA, so I have 1 plus L times this capacitance I have as total capacitance. And that is CISS, what I would like to have, because this parameter is unity. Then we are going to, so this is another circuit. This is just a circuit that I just evaluate. Here the antenna dot circ to get the parameters for the antenna. And then I'm going to use them in the other, in another circuit, in the noise circuit. So in the noise circuit that I showed you in the presentation. Oh, sorry, that is this window. So here the CA and the LA, etc., are put in as parameters from the result of the calculation. I make the DC gate current 0, so we don't have to do with that noise. And I want to have some numeric values for the Boltzmann constant and the temperature, and they are in the program, so I just can get them from them. And then I can calculate, basically, from the expression that we saw last time, the equivalent noise resistance that I would like to have. And this is what I'm going to use to evaluate the noise performance. So for all the widths, I'm done calculating first of all, I'm calculating the length that makes the input capacitance correct, gives it the correct value. And then I'm calculating the current that I would like to have the noise floor as low as possible. So I set the input capacitance of the FET equal to the total source capacitance, which means I will have the lowest 1 over F corner frequency. So if this corner frequency then is too high, there's nothing you can do. You have a showstopper. That is the reason why I do so. So if there is reserve later on, you might for some reason decide to make the capacitance, to give it another value, to use a shorter transistor or a narrower transistor, as long as we are in spec. But here we start with the optimum, because if the optimum isn't good enough, we know we have a showstopper. So here I calculate the total capacitance, and I solve the thing that I need, and then I'm going to calculate the total equivalent noise resistance as a function of the drain current. From this, I have a requirement for this total equivalent noise resistance that was done before, and then I can just solve the drain current. You can solve using symbolic Python here, sp.solve. This is done with symbolic Python, but it is much faster in Python if you have only 1 or 2 variables. And here we have only 1 variable. We want to solve ID, and I'm carefully making my expression such that only the drain current is symbolic in the expression. Then I can use the lumpdify function and use numeric Python, which is much faster. and then I can solve it. And this function is already included, so you don't need to import it with NumPy. And then I have the drain current, and I'm going to list everything and plot everything. That is basically what we are doing. So if I would run the program now, it would do everything for me. It calculates the antenna capacitance. Unfortunately, I cannot increase this window, I guess. But oh yes, I can. I can. Fortunately, I can. So it doesn't increase the plot, but the plot we have in HTML as well. So it gives you this list of width and length and things that it all calculated, and the plots. And you see for the three cases, the plots are on top of each other, which means you are free to select any of the three. They have the same noise performance as expected, of course, because I'm solving the same equations. I only have another start value for the width. That is basically what we are doing here. The noise, I think it's better to go to the HTML, because then I can show you this graph a little bit wider. You see they're all on top of each other, more or less, and the value here is should be 25 times 10 to the power of minus 18, and it is a little bit more. It's 28. Otherwise, it should be a little bit lower. But let's say for a first guess, that is good. This is good enough to start. And now you might wonder, does this match also on, let's say, if we are going to go to, for example, LT-SPICE and we're using a BISIM model? Well, the idea is that the parameters of the EKV model that are in SliCap have been tuned so that I have the same result in the in SliCap as in LT-SPICE, of course. And then I don't have to do the biasing in SliCap, and that is, of course, the advantage of using SliCap at this stage of the design. But for the sake of completeness, I would like to show you also the result in the thing with LT-SPICE. And there's a nice thing. Well, maybe it's not nice at all, but there is something to learn from. Let's say if you go to the definition of, so this is the circuit we used before. Oh, I didn't put the capacitance in it. That is unfortunately that I should have done. So the outcome will be a little bit different. I need to put the capacitances in parallel with the signal path, but I just took the circuit that we used before. If you go to the MOSFET, you see there is the length and the width and the multiplication factor defined, but not the drain area and the source area and the drain parameter and the source, which means that in fact, it cannot calculate all the resistances of the drain and the capacitances of the drain. That is, in fact, this is missing. Maybe that is the reason that the model is a little bit strange if you don't apply an extremely small negative bias on the bulk. And this is nice to show you because it's one of the lessons is that you should always verify your models. If you have measurement data, always try to make a simulation in which you check, does the measurement data correspond with what my model is telling me? Now, if I'm running this one, oh, it doesn't want to run this one. It shows everything I have, but okay. I want to add here view traces, add traces, the input noise. Okay, and then I will make it large and we don't see all the other stuff. And you see, indeed, it is about 5.3 nanovolt per square of hertz. It will be larger because I forgot CF. So I must be fair with you. It will be a little bit larger. And this is just because a mismatch of the model used here and used in SlideCap. But now, if I do this without the negative bias, so remember it was 5.3. So if I change this one to 0, so you just connect the bulk to the source, then there is something wrong with the small signal model. And I've detected that earlier with this parameter set, but still using the parameter set because this one is free for to use for educational purposes. So now we run it again, and I add trace the input noise, and now you see it is much and much higher. It is 7.4 nanovolt per square root of hertz, only because the bulk is not 10 millivolts negative. It can be a result of the source resistance that is not correct, because I didn't do all the specifications for drain and source terminal. Okay, this is something you have to be aware of if you use this library. The nice thing about this library model that we use here in SlideCap is that it has the drain-induced barrier model reduction modeled, and that lowering. So that is a thing that other models don't always have, and it also has breakdown modeled in the FET. So it's a quite complete model, but there's something wrong with the small signal behavior if you don't put a small negative bias on the bulk. And that is just nice to know. Okay, so this is basically the verification of what we did with SlideCap. And apart from the fact that I forgot CF, it's quite close in the region where we want to have it. So for now, I say it's good enough. So we have a starting point for the design of the first stage, and we can go to the next step and in the design. And the next step is the design of the output stage.